Okay, so on this is 3.9. There's no Math Excel on 3.9, and there's not an additional vocab support for this one. It's just reteaching and a Form K. So this is a little shorter packet instead of having two packets like y'all normally do, based on the nature of this lesson. So the reteaching part shows you your theorem, or in this case postulate. So this is like printed notes for you. Through a point not on the line, no line is parallel to the given line. And in spherical geometry, lines are great circles, and they always intersect in at least 2 points. And since all lines intersect, they cannot be parallel. So that's all your spherical postulate. And then the Euclidean parallel postulate that we did a long time ago was, in Euclidean, there's exactly one line that's parallel to another that contains a point that's not on the line. Okay, so here's a sample problem. Can any line be drawn on a sphere such as the Earth, such that it's parallel to another line on the sphere for all points on each line? And since all lines are great circles, the answer is no. All lines intersect at least twice. Okay, so now for the exercise, draw an example of parallel lines that illustrates the Euclidean parallel postulate. Okay, so the Euclidean one is like, say you have a line like right there. Okay, so you draw a line. You have a point that's not on the line, like point P. I just put it right there. There's only one line that's parallel, so just make it like that. And so these would be parallel. So that's an example of the Euclidean parallel postulate. Remember, we used this with an auxiliary line. We used that with an auxiliary line before, which was like this one parallel to that one. That's where we used it before. This is the only part you have to write. Bless you. But we used it before with an auxiliary line. Okay, the next part says draw an example of two lines that illustrate the spherical parallel postulate. Okay, so on this one, I'm going to let you abbreviate it. This is a good drawing of it. So if you want to, just do that. Or if you'd like to draw your circle, and then you draw an ellipse, and then draw another one that has a dash. You know, that's basically it. So if you just want to put your arrow, that's fine. Or if you want to draw, you can. So I basically tried to make my drawing look like this. So draw a circle, then draw an ellipse, and then draw a tilted ellipse. So that's what I tried to do here. Okay, so the next part, whoops, excuse me. Okay, so for the next part, this is your triangle angle sum theorem. And so basically on spherical geometry, it's always greater than 180. Lines are great circles, so the sum of the angles is always greater than 180. In Euclidean, it equals 180. Let's skip the sample problem and get to the exercises. Okay, so this is pretty typical of what you would see on like the review or on the test. For each set of 3 angle measures, does it exist in Euclidean, which means it equals 180? Does it exist in spherical, which is greater than 180? Or is it neither, which is less than 180? So you ought to mark that so you know. Euclidean equals 180. Spherical greater than 180. Neither is less than 180. And then all you do is use your calculator and add. So if you add these 3 together, you get 169, and so it's neither. On the next one, you add those 3, you get exactly 180, so that's Euclidean. On the next one, you get 300, and so that's spherical. On the next one, when you add up these 3 numbers, you get 363, so that's spherical. Notice that it could be spherical if it's just bigger than 180. There's no specific number it has to be. Okay, now this one, 30 and 40 is 70. 70 plus 50 is 120. So then it's neither. Triangle doesn't exist. This one would be 100 plus 80, or 140 plus 40, so that's 180. That's Euclidean. This one would be 90 plus 90, which is also 180. So that's Euclidean. This one, when you add up all 3 of those numbers, you get 249. So that's spherical. And this one, you get 100 plus 160, which is 260. So spherical. So again, all you do is add. No subtraction at all. Okay, so number 12 are lines of latitude examples of great circles. So the first thing we want to put for this is a great circle must go through the center. That's one of your definitions. A great circle must go through the center. So, in other words, if you had this and it went through the top, that's not a great circle. It would have to go through the middle. Either the middle this way or, that way. So the first thing is a great circle must go through the center. So the question with regard to latitude lines is going to be no, it's not a great circle except for the equator. Latitude, the answer is no except for the equator. Longitude, on the other hand, is different because those are more vertical. Whoops. Really. Longitude is going to be yes, all pass through the center. Longitude is yes, all pass through the center. So this has a pretty decent drawing. I'm not going to draw it. So your latitude lines, as you can see, are the horizontal ones. You'll see that? And the longitude ones are the ones that are kind of like vertical, but they look like arcs a little bit. And then the equator's the middle. So these are not great circles, but the equator is, and then the longitude would work. Okay, so now we're done with that side. So now we're on the form K. In Euclidean geometry, how many lines are perpendicular and sketch? So there's only one. And an example of that would be, say we have this line, which is L, and we have a random point P. Now remember earlier we talked about there's only one that's parallel to it, which would be this way. But there's also only one that's perpendicular. So there's your drawing. Any questions? So there's only one. Okay, the next one says a triangle has two angles with measures 43 and 51. What is the measure of the third angle in Euclidean? So for that, you would do 51 plus 43 is 94, and then 180 minus 94 is 86. So 86 degrees is your answer. So remember, Euclidean is when it's equal to 180. Spherical when it's greater than 180. So what is the measure of the third angle in spherical? It's anything bigger than 86. So any number above 86. Or you could say x greater than 86. So that's the difference. Euclidean has to be exactly 180, but spherical has no upper boundary. Then number 3, what is the sum of the measures in the triangle? So again, you could think of these as like pieces on a volleyball or a beach ball or a basketball. And you just add these numbers together, you get 249. And this one, you add your two 90-degree angles, you get 180 plus 80 is 260. So remember, in spherical geometry, it's possible to have 2 or even 3 right angles. Okay, the next one says 3 angles are given. Does it exist in Euclidean, which is when it's equal? Spherical when it's greater, or neither when it's less? Okay, so you add these numbers up. I'm going to save time. I know that it's not even close, so that's spherical. Whatever it is, it's much greater than 180. Okay. And this one's not even close. Whatever it is smaller than 180. So that's neither. This one, if you add 71 and 19, you get 90. 90 plus 90 is 180. So that's Euclidean. And this one's not even close, it's spherical. If you have two obtuse angles, you know for sure it's spherical. Okay. Now this page says explain how each property of Euclidean compares to what's true in spherical. So all of these are true in Euclidean, and we're trying to figure out, how spherical compares. So number 9, there's only one obtuse angle in a triangle. So in spherical, you can have 2. In spherical, you can have 2. Between 2 points, there's exactly one line. In spherical, you have an infinite number of lines. Infinite number of lines. There's no A in infinite. I'm not going to count off for spelling, but I've seen it before with an A. Infinite. Number 11, the angles in a triangle add up to 180. I'm just going to abbreviate putting an S instead of writing out spherical. This would be greater than 180. Greater than 180. Number 12, 2 lines intersect at exactly 1 point. And so for spherical, it's at 2 points. That's the one that we showed, like if you have 2 planes or 2 hot air balloons or 2 birds that intersect at right angles. The answer would be 2. Okay, number 13. There's only one line that connects 2 points on a circle. In spherical, that'd be an infinite number that connect 2 points. Also, just to show you what 13 means in Euclidean, it's like that, which would be a chord. And a certain type of chord is a diameter. Y'all know about a diameter being through the middle. So that's what they're talking about. Only one line connects 2 points on a circle in Euclidean, and that's this part. But in spherical, there's an infinite number. Okay, number 14, what is a great circle, and how does this circle compare to others? A great circle is the intersection of a sphere and a plane that contains the center. So that's your definition of great circle. A great circle is the intersection of a sphere and a plane that contains the center. How does this circle compare to other circles that can be drawn in a sphere? It is the largest. Since it goes through the center. It is the largest since it goes through the center. So in other words, if I sliced this like this, this would be bigger than this one. Okay, then number 15. This is open-ended. Name 3 possible angles of a Euclidean triangle. Imagine a triangle from spherical having 2 of the same angles. Explain what the third angle could be. So one we used in one of my classes was just the 30, 60, 90. (30, 60, 90) is a random example. And then an example in spherical would be 100, 60, and 90. It wanted 2 of the angles to be the same, so the one that's different is the 100. And then it says explain also. Or anything above 30. Any number above 30. Okay, so now we're done with 3.9, and there's no Math Excel on it.